right, Tuesday is a big day. You've got an exam and a homework assignment due. Here's a little bit of information about the exam. It actually has a pretty narrow focus. It's only going to include lectures 10 through 16, which is today's class period. So it should be relatively easy to study for the exam since it's pretty narrowly focused. I've mentioned which book chapters that's covering. And like the previous exam, there's going to be two sections, a conceptual part of the exam where it's related to short answers and you trying to describe and explain different phenomena that we've studied, and then the second part of the exam will be problem solving. And so it's likely that you'll have questions where you may want to use Microsoft Excel, and you can also prepare a page of notes that you'll use for the second part of the exam. You can't use your notes during the first part of the exam. But just as a reminder, since I'm trying to see what you can do during the exam, you can't use any pre-existing spreadsheet files. And so if you have a homework spreadsheet that you created when you were using unit hydrographs, for example, you can't refer to that during the exam or alter it in order to solve the exam problem. You have to start from just a blank spreadsheet during the test. So that's what we'll be doing next Tuesday morning. Any questions about the second exam? We're going to continue talking about hydrographs today. Last time we discussed unit hydrographs, and a unit hydrograph, remember, is prepared when you have a known response in a watershed to either 1 inch or 1 centimeter of rainfall. But it's often the case that you don't have that information available. Sometimes you may not have the stream flow data because a project is just newly of interest or it's inaccessible. And so when that's the case, when you don't have the information you need to apply a unit hydrograph, then you can generate what's called a synthetic hydrograph. And a synthetic hydrograph basically takes watershed parameters like the area of the watershed and the length of different streams, and it extrapolates those parameters based on what's been observed in the area, just sort of the known regional response. And so if you had a watershed 10 miles away that had about the same slope, about the same curve number, it was very similar, and you knew how it responded during a storm, you can apply some of the same empirical factors from that watershed to the watershed that you're interested in, and then generate a hydrograph. And so that's the procedure we're going to go through today in class. One of the two things we're going to be covering is a synthetic hydrograph procedure. And Snyder's method is really old. It actually comes from the 1930s. So it's been around a long time. It's nothing new that they've wanted to know how a watershed would behave during a storm. And you'll notice that the hydrograph has a triangular shape. And what Snyder's method does is, based on some of the parameters for the area that you're interested in, it calculates what's known as a standard storm duration. And I guess I should refer to the figure here. We've got a hydrograph and a hydrograph above that. And so remember, the hydrograph is talking about the rain, and the hydrograph is talking about the runoff. And so this is sort of a two-part procedure that we're going to be stepping through. I've given you a handout just now that I've tried to fix some of the errors that exist in the textbook. I love our book, but this is one of the sections in the book that has been sort of consistently a problem. In fact, I was tempted to completely remove this method from what I teach you, but I decided instead to try and clean it up a little bit, and I spent a couple of hours yesterday trying to work through the kinks. So hopefully today's example will be better than it has in the past and will help you understand how this procedure works. But when you're going through based on the parameterized data that you've got for whatever the watershed of interest is, you'll calculate some standard storm duration. And that may not be related to the storm duration that you're interested in. So I can have some watershed, and just based on the area of the watershed and how it compares to other watersheds in the area, when you go through the Snyder method, it may say, all right, well, let's assume a storm duration of 0.63 hours. and that's not actually a storm duration that's useful for you. Maybe you're more interested in what happens to this watershed during a 1-hour storm event. And so one of the steps we're going to go through is converting the standard storm duration into a desired storm duration. And then the other thing that we're going to have to do is just go through a series of empirical equations to try and find the peak flow rate, QPR. All right, so the handout that I've given you includes a lot of the variables and the descriptions for each of the formulas along the way. And one of the unfortunate things about it is that the variables are very similar. So you'll notice, for example, that if we look through here in step 1, it refers to something that's T sub R. And then in step, where is it? Oh yeah, step 2, in step 2 there's T sub R, but it's a capital R instead of a lowercase r. And so that's a bit confusing when you've got two different T sub R's. So we'll have to pay careful attention to the difference between the two of them as we go through the example. So let's do that. We've got a watershed that has an area of 5.42 square miles. And in the handout I've given you, I've identified both the SI constants and the BG unit constants that you have to use as you're going through here. And so this is going to be a BG example, but your homework problem is in SI units. So you're going to be taking down notes as we work through this example. Be very careful not to follow those notes literally when you're doing the homework assignment, because there's different constants if you're in SI units. Okay, so we've got a watershed area of 5.42 square miles. The main channel length is 4.45 miles, and that's referring to the largest stream that runs through the body of the watershed. And so the regional parameters that are taken from similar watersheds in the area, the C sub T and the C sub P, those will just be given to you in the kind of problems you're likely to see. It would be a pretty advanced thing to try and develop these parameters for a watershed, so we won't get into that level of detail. What we're going to do is, first of all, find the standard duration for the storm, and then with our desired storm duration of 30 minutes, we're going to find out what the hydrograph actually looks like in that storm. So we'll follow through the steps, starting with step 0, where we just sort of lay out all the data in a single place. The area is 5.42 square miles. The length is 4.45 miles. L sub C is 2 miles. C sub T is 2. And C sub P is 0.625. All right. Step 1, we're going to first of all find the standard duration by calculating the time to peak. T sub P is C1, C sub T, L times L sub C to the 0.3 power. So here that's 1.0 times 2.0, 4.45 times 2.0 to the 0.3 power. So that gives us a time to peak of 0.3853 hours. 3.853 hours, and that's the time to peak. It's just given. Yeah, it's a given value. In the handout, it gives you the, it's a coefficient based on what unit system you're using to try and make the units work out. So on the handout it says that C1 is 1 for BG units and 0.75 for SI units. Yeah. Now this is the time to peak of the standard storm, which is not what we want yet. Okay. And we convert that to T sub r. This is lowercase r. It is T sub p divided by 5.5. So 3.853 hours divided by 5.5, 0.70 hours. So that's the standard storm duration. So just based on the shape of this watershed, this method assumes a certain duration that would go along with a typical hydrograph. And so it's going to be very, very uncommon that the standard storm duration is equal to the desired storm duration. And so we have to translate the two. And that's what we're going to do in step 2 here. And if you follow along on the handout, it says determine the time to peak T sub p, capital PR, in hours for the desired storm duration T sub r in hours. So in this problem, it says to find the synthetic hydrograph for a desired rainfall excess duration of 30 minutes. So our T sub r with capital R is 0.5 hours. That's given in the problem statement. That's what we want to know, how the hydrograph looks like for that duration of storm. So T capital PR is T sub p plus 0.25 times T capital R minus T small r.
Why would we not use the 1 hour in part A? Or is that not even relevant to the problem?
No, that's a good point. I changed the example without changing the slide. So we'll come back around. We'll do part B and then we'll do part A.
Okay.
Yeah. Yeah, thanks for asking that. Yeah. So he was asking why is it that we aren't considering the 1 hour storm duration, and that's just that this slide I didn't update along with the handout that I did. So we will find the 30-minute hydrograph and what that looks like, then we'll go back through and find the 1 hour hydrograph. Okay, so for the desired storm duration of half an hour, then we can find the T sub PR. The T sub P that we've just calculated is 3.853 hours plus 0.25 times T sub R, which is a half hour, minus 0.70 hours. And that is going to give us a T sub PR of 3.803 hours. Okay, now step 3 is determine the peak discharge, Q sub PR. Find peak discharge. Q sub PR is C2 CP A divided by T sub PR. Okay, so if you look on the handout, it says that C2 is going to be 640 for BG units. So 640. We're given a C sub P of 0.625. And the area is going to be in square miles since we're BG units, 5.42 square miles. And then dividing it by T sub PR, which we just calculated as 3.803 hours. And that means that for the 30-minute hydrograph, we are going to have 570 CFS per inch as the peak. What we've defined so far is just how high the hydrograph is. We haven't yet defined the width of it, this bottom dimension here, T sub B. And the process that the Snyder method goes through for identifying that is just finding the width of the hydrograph at certain flow rates. At 75% of the peak and half of the peak, you find how wide is the hydrograph, and then use that to calculate the entire hydrograph duration. That's right. And that's why we've been using all of these empirical factors along the way, like 640. That's the conversion factor that gives us CFS per inch as the output unit. Yeah, if you look at step 3, it gives you the units there. It'll be cubic meters per second per centimeter. All right, so what we're going to go through next in step 4 is finding the width of the hydrograph at certain locations. We're going to find the width of the hydrograph at a flow rate of 50%, and that's C50 divided by QPR divided by A to the 1.08 power. So that means the C50 that we're going to use is 770 for BG units. That's on the handout. 770 divided by 570, which we just calculated, divided by 5.42 square miles, and that's to the 1.08 power. So from that we get 5.045 hours is the width of the hydrograph at 50% flow rate. Means that during the storm, there's going to be a period of about 5 hours when the flow rate is at least 50% of our peak flow rate that we just found earlier, which was 570 CFS per inch of rainfall. W75 is 400 and, well, the formula for W75 is C75 divided by the same Q sub PR divided by A to the 1.08 power. So this time it's going to be 440 divided by 570, 5.42 to the 1.08 power. And the W75 for this one is 2.883 hours. Okay, so now we can go through, and the last thing that we need to know is how wide is the base of the hydrograph. We already know its height, and so in step 5 we're going to be calculating the, I go back to this, the base of the hydrograph, and then I've already calculated the parameters I need to know, the T sub P, capital T sub P. And you'll notice that T sub R, that's the storm duration. We said in this illustration, let's consider a storm that's 50, that's half an hour, so 0.5 hours. And we also already found T sub PR. That was here in step 2. And so obviously T sub P is just half of the storm duration plus T sub PR. So that's the other thing we're going to do in step 5 besides calculating the T sub B. Okay, so the formula for T sub B T sub B is C5A divided by QPR minus 1.5 W50 minus W75. The handout says that when you're in BG units, you use 2581 for C5. So 2581. Again, in your homework, you're going to be working in SI units illustration, so that will be 11.11 instead of 2581. So 2581 times 5.42 miles squared divided by the QPR, which is 570 CFS per inch, minus 1.5 of the W50 we just found, 5.045 hours, minus the W75 we just found, 2.883 hours. And that works out to 14.09 hours. And then T sub P is T sub R divided by 2 plus T sub PR. So the T sub R that we had gotten earlier, half-hour storm duration. So dividing that by 2, it's 0.25 hours plus the T sub PR was 3.803 hours. So that's going to be 4.053 hours, right? Yeah. So when it says to determine the hydrograph, what that means then is that you have to put together a little drawing. So here is our drawing that shows, first of all, our hydrograph is 0.5 hours. And how much rainfall occurred during that 0.5 hours? Well, this is a unit hydrograph, and so we assume that there was 1 inch of precipitation during half an hour. And then the response that it caused was the peak is going to go up to 570, and the time to peak from the beginning is 4.05, and the total base length is going to be 14.09. So it will look like this dimension, 14.09 hours. This is 4.053 hours. And then the peak flow rate was 570 CFS per inch. Okay, so I've just illustrated that on the handout. What we did was part B. Why don't you go through the same process using a desired storm duration of 1 hour. Most of these things will still be the same, but in part A, we're not looking for a half-hour storm duration. We're looking for 1 hour storm duration. And what you'll notice is that it has a very minor effect on the hydrograph. You're changing 1 inch of rainfall in a half hour versus 1 inch of rainfall in an hour. You'd think it would have kind of a major effect, but it doesn't actually. So let me pause the recording and stop talking for a while, and I'd like you to go through the same process, but do part A, where we're assuming that the T sub R is 1 hour instead of half an hour. All right, many of the numbers stay the same as we're switching from desired storm duration of ½ an hour to 1 hour. So it's just sort of plugging in new numbers along the way. So I haven't written everything out over again. I've just written the resulting calculations when you do those new substitutions. You get a T sub PR of 3.928 hours. Now, as we'd expect, the peak discharge is going to be lower. And so think about why that might be. If you've got an inch of rain that's falling within ½ an hour, then that means there's a greater intensity of the storm, so the peak discharge is going to be correspondingly more intense. Then if you spread that same inch out over 1 hour, then it sort of lowers the intensity of the precipitation, reduces how much runoff is going to arrive at the outlet at any particular locations, at any particular time. So the peak goes from 570, which is what it was when it was an inch of rain in ½ an hour, down to 551.9 CFS per inch, which is the peak runoff when you're spreading out that inch of rain over an hour instead of a ½ hour. We find these width parameters, 5.22 hours for the width of 50% flow, width of 75% flow, 2.985 hours. And so the T sub B, the base duration, is going to be 14.53 hours instead of the 14.09 hours. And again, that makes sense that if you spread out how long the rainfall is, you're going to be delaying the end of the runoff as well. So it takes about a ½ hour longer for the hydrograph to finish draining because the storm duration was a ½ hour longer. So it's no coincidence that it's added on only about a ½ hour, a little bit less than a ½ hour as a matter of fact. And so the same thing, there's a delay in the time to peak, and I've drawn the new unit hydrograph on the board here. So I've shown you how to switch around the storm duration, but what about if it rained more than an inch? And this has been the development of a unit hydrograph, which is saying we have 1 inch of rain that's falling in 1 hour for the case of the calculations in red on the board. What if it was 2 inches of rain? What would the hydrograph look like if it was 2 inches of rain in 1 hour instead of 1 inch of rain in an hour? What would you do to the shape of the hydrograph? It wouldn't be wider. It would only be taller. Remember, a unit hydrograph, the idea behind a unit hydrograph is that if you have double the rain, then it just doubles the vertical dimension. And, you know, in reality, we know that if you have more rain, it's going to take longer for the watershed to drain, but we sort of set that aside and assume that the travel times are the same, but the peak runoffs vary when you increase or decrease. And so, you know, the process we went through with the spreadsheet last week, we just kept repeating the same hydrograph over and over again, regardless of the amount of rainfall. The duration of the storm was the same. You know, remember, during each of the 4 periods, there was 4 different time periods, and we copied, basically we were copying and pasting the hydrograph shape, but we were delaying it by an hour as we went from column to column. And so the length of each of those storms was the same, but we just scaled the runoff amount by however much there was. If there was 0.2 inches instead of 1, we multiplied the hydrograph by 20%. And so if we had 2 inches of rain during an hour, then our peak runoff for 2 inches of rain would just be 2 times 551.9. And the duration would still be 14.53 hours. This is a unit hydrograph. So any questions about this process or the example that we've just gone through? All right, the other thing that we're going to do today is learn about what's called an S-hydrograph. And the purpose of an S-hydrograph is what if you're given a unit hydrograph and it's not a Snyder unit hydrograph. The Snyder unit hydrograph has its own way for adjusting storm durations, but if you had a unit hydrograph that was based on actual data from the field, like the kind of thing that we did in the last class period, but it is based on a storm duration that you need to change. You know, if you have a unit hydrograph that was based on a given storm duration of 2 hours, but you wanted to find out what would the shape of the unit hydrograph look like if it was a 4-hour duration, then this S-hydrograph method is an approach that allows you to translate the shape of the hydrograph for different storm durations. And so remember, there's two main things when you've got a unit hydrograph. The storm could either be more or less, so it's the vertical dimension in terms of the peak flow rate, or it could be longer or shorter, the storm duration that's causing this runoff. And so this S-hydrograph approach is allowing us to handle a different hydrograph that generated the hydrograph to begin with. And so this S-hydrograph method, this is completely separate from the Snyder approach. This S-hydrograph method kind of harkens back to what we were doing last time, because it was last time that we were working with hydrographs that were generated based on field observations. So what you'll notice is that if you overlap hydrographs multiple times, then add the shape of those hydrographs together, what you end up with is something, a shape that ultimately tapers off and plateaus, where the flow rate isn't increasing anymore. And it's saying that if you had a storm of, let's say, 2 hours, and you kept having 2-hour storms back to back to back, well, the hydrograph shape here, it hasn't finished draining by the time the 2-hour storm duration is over. You know, the storm event lasts for 2 hours, but the runoff event, in this little illustration, it seems like maybe the runoff is taking 6 hours approximately. And so if you layer and delay 2-hour rainfall events over and over again, then you can use this S-curve in order to generate a new resulting shape. And so we're going to go through a spreadsheet process today. That's why I asked you to bring your computers, is for the spreadsheet work we're going to do in just a minute to try and translate unit hydrograph durations. So here's an example of a conceptual question that I could ask on an exam. Is I could ask, what's the purpose of an S-hydrograph? You know, it's one thing to be able to just understand a method and mimic the method. That's what a parrot does. A parrot doesn't know what it's saying. It just hears something and repeats it. And I want you to be able to do more than parrot spreadsheet techniques. I want you to understand what they're used for, because you know, often you may not have a reason to apply a method. You know, sometimes you'll say, well, this looks like a case where I could apply an S-curve, but unless you know really what the S-curve's trying to accomplish, you may try and apply different procedures that you've learned in your engineering education in cases when they don't apply. So here's the procedure that we're going to follow in order to translate the storm duration of a unit hydrograph, which is the whole point here. What we know, the given information, is what happens during a 2-hour storm. So during a 2-hour storm, this is what the watershed does. If there's 1 inch of rainfall during a 2-hour storm, then it looks like it takes about 22 hours for the watershed to drain. But what we're interested in is, how would this watershed behave if you still had 1 inch of rainfall, but instead of that occurring during 2 hours, what happens if you have an inch of rain during 4 hours? It's not just as simple as like doubling the length of this. We have to have like a methodical technique that we'll be following to do that. All right, so the first step that we'll go through is create the S-curve. And the conceptual drawing that I showed you is that you basically just repeat them over and over again. And so let's actually start up Excel as we go through this procedure. And we need to have the given data and type it in. So we're going to have time in hours, and then the flow rate, CFS per inch. And you'll notice that this is going in 2-hour time increments. Okay, so this is just the 2-hour unit hydrograph that we start off with. And the procedure says that what we're going to need to do is lag it by 2 hours. And so we copy this, Control C will copy it, then Control V will paste it, and we just keep lagging it over and over again. I'm going to move this out of the way. And basically we have to do it not an infinite number of times, but enough times that the start of the storm corresponds with the end of the storm over here in this column. So we're going to have to make it so that the 0 is matching up with the 0 down here in 24. And that might overdo it a little bit, but better to have more than you need than not enough. I'm going to change the column width just so that we don't start working off the page. Okay. So let's add everything up and see what we've got, what the shape of it looks like. So I'm going to have a column where it's just the sum of everything to the right of it. So equals sum of, and I'm going to include everything, including the original 2-hour unit hydrograph. And what it should do, we're hoping, is plateau to the point where it gets to some maximum amount and stays there for a while. We probably need to put in a few more columns because it gets up to a maximum value and then it starts going down again immediately. So let me just insert a few extra columns here. All right, and then we're going to continue to paste the hydrograph a few more times while we lag it. We're going to have to update the formula to include these extra columns that we've just added. So if I go back over here, I want it to include all of these columns. Okay, and I can drag that down through. All right, so now you can see it reaches some maximum of 2015, and it stays there for a while, then it starts going down. So we created a S-curve, and now we need to lag the S-curve. We need to shift it by T prime R. And T prime R is the storm duration that you want. And we want it to be a 4-hour storm duration. And so what that means is that we're going to have to shift the hydrograph that we've just created by T prime R. So we're going to copy it, we're going to create a copy of it, and we're going to move it down. So here's the S-curve. S-curve is the title of this column. And then we're going to call this the shifted S-curve. And it's introducing the 2-hour unit hydrograph. 2 hours is the original duration, T sub R. So T sub R is 2 hours. And then T prime R, which is the desired duration, is 4 hours, just for references. So we have the S-curve, and now we need to shift it by 4 hours in this next column. So I'm creating a copy of it, and I'm going to paste the values. And this is important because if we just paste like normal, it's going to paste the formulas, and it's not going to work out the way that we need it. But we need this to be not just 2 hours lower, but we need it to be 4 hours lower. So we're going to paste the beginning of the hydrograph here in hour 4, and I'm going to paste the values, not the formulas. So if you look, when I right-click for paste, it gives you some options here. Boy, it's sort of spastic there. All right, paste special. I want it to paste the values. And so it's the same numbers as before, but it's lagged by 4 hours, which is the, if you look at the procedure, it says shift the curve by T prime R. So now this is the shifted or the lagged S-curve. Okay. And now we have to subtract the two. We have to subtract the S-curve and the lagged S-curve. Subtract the lagged S-curve from the original S-curve that we calculated. And so for this next one, I'm going to call it S-curve minus lagged S-curve. So equals that minus this. And then we can drag that formula down. Now here where it becomes negative again, this is irrelevant. So I'm just going to delete all of these values where it's dipped into negative territory. The heart of what's going on is up here when it goes from 0 and then back down to 0 again. So let's just pause right now and take a look at where we started and where we're at. We said that our beginning point was when there's an inch of rain during a 2-hour period, this is what the watershed does. But we want to know, what does the watershed do when there's an inch of rain in 4 hours instead of 2 hours? By the way, if we want to know the volume of runoff, how would we do that? Because I need to illustrate something for the last step that we're going to take in fixing this. Remember, volume is flow rate times time. So each one of these these are 2 hours apart. And so if I wanted to know the volume that happened during each of these, it would be 69 CFS, it's cubic feet per second, times however many seconds there are in a 2-hour time period. And so the volume would be equals 3,600, which is how many seconds in an hour, times 2. So that's how many seconds are in a 2-hour time period. And then times the sum of all of these. And that'll tell me the total volume of runoff during the storm. So this is the volume in cubic feet. And if we look at this translated hydrograph that we've just come up with, where we subtracted the S-curve from the lagged S-curve, it has, here's the time 0. So the peak flow rate, the highest flow rate that we're going to see is 741, whereas the highest flow rate here was 389. So something's not right. That's why we've got to do this final step, is that here we have an inch of rain in 2 hours should have a higher peak runoff than an inch of rain in 4 hours. So the last step that it says here, step 4, divide the new hydrograph by T prime R divided by TR. We're going to have to divide this hydrograph by 2, and the reason is that the volumes are off. If I was to calculate the total volume of this, it would again be equal 3,600. Let me just indicate that this is volume. And then I'll do this below it. Equals 3,600 times 2 times the sum of all of these values. I didn't close with the parentheses. So the volume is double what it ought to be, because you're going to have the same amount of runoff. It's just occurring over a longer period of time if it rains during 4 hours instead of raining during 2 hours. And so we can know by looking at the peak flow rate, or we can know by looking at the volume, that we have to make one final adjustment. And so what the instructions tell us is divide the new hydrograph by T prime R divided by TR. So TR for us was 2 hours, and T prime R was 4. So we have to divide by 2, which is the ratio of the desired runoff duration and the given runoff duration. And so the final step for us is the divided by 2. So it's going to be this divided by 2. And it won't always be 2. It's 2 because our T prime R is 4 hours and T sub R was 2 hours. So we're sort of running off the screen now. Here is time, row 5 is time equals 0. So let me put the time over here again so that we can see time in hours. It was 0, 2, 4, and so on. So when you get the inch of rain in 2 hours, your peak flow rate is going to be 389. And that happens during hour 8. The peak flow rate here is going to be 370. So the peak flow rate is lower, as we'd expect, and it is later. It's at hour 10 instead of at hour 8. So this is the new unit hydrograph. So this would be the answer to that example. Yeah. No, that was just to illustrate why we had to do this last thing of dividing by 2. Yeah, it was to illustrate that if you don't divide by 2, you're going to be saying that there's twice as much runoff as there ought to be. And we know that you're not going to have more runoff. If anything, you'd have less runoff by by having a 4-hour rainfall duration instead of a 2-hour rainfall duration when it's the same total depth, when the rainfall depth is still just 1 inch. So this is the process you need to go through on the last homework problem, on homework problem 3. Excuse me? I can't hear you.
The volume of the highlighted column.
Oh yeah, let's calculate that just to see. I mean, we don't need to know it, but it should match the first column. So equals 3,600 times. Yeah, I suppose we could just drag that over. So all it's going to be doing is looking at the 145.08. Should be close. Yep, 145.08. It's just when the rain falls is different. We're changing the temporal distribution, but not the total volume of runoff. All right, so that's all I have for you today. Remember that Tuesday's a big day. You've got that homework assignment due. We are having an exam. So let me know if you've got any questions on the homework.